In this video, we will talk about level curves and how they can help us draw 3D graphs. So a level curve of a function f of x comma y is a graph of f of x comma y equals c, where c is a constant. So when you set your function of two variables equal to some constant, what we get is an equation with two variables, an x and a y. So this graph is going to be something in the xy plane. All right, so let's look at an example and then see how this will help us draw the graph, draw the 3D graph once we draw the level curves. Okay, so I want to draw the level curves of f of x comma y equals x squared plus y squared for the following values of c. Okay, so let's first do it for c equals -1. So once I have my value of c, I just set my function equal to that value. So this will give me x squared plus y squared equals -1. And when I look at this equation right here, this actually has no solution. No solution, since when you square a real number, it's going to be non-negative. So x squared is non-negative, y squared is non-negative. So when you add them together to get x squared plus y squared, that's going to be non-negative as well. It's going to be greater than or equal to 0. So there's no way it can be equal to -1. All right, let's move on to the next c value. So let's do c equals 0. So if I set my function equal to 0, we get x squared plus y squared equals 0. And with this equation, there's only one value of x and y that satisfies this. The only thing that works is if x equals 0 and y equals 0. If I try anything else, any other combination, the left-hand side is going to end up being positive. There's no way to make it 0 unless both x and y are 0. Okay, let's move on to c equals 1. So now I'm going to set my function x squared plus y squared equal to 1. And for this has a more interesting graph. This is actually a circle. This is a circle, so I can describe its center and its radius. So the center and the radius. The center of the circle is 0, 0. And the radius, remember that this 1 is r squared, the radius squared. So the radius would be the square root of 1, which is just 1. All right, so now let's look at c equals 2. c equals 2. Let's set x squared plus y squared equal to 2. And this also is a circle. So we can write down its center and its radius. The center of this circle is going to be the same. It's at the origin, 0, 0. And the radius of the circle, remember that the 2 is r squared. So square rooting that would give us the radius. So the radius is going to be square root of 2. So it's a slightly larger circle than the previous one. All right, so now let's draw these, because the example said to draw the level curves. Okay, so let's draw some axes. So I'll have a y-axis and an x-axis. So going back to what we found for our level curves, when c equals 0, that corresponded to just a single point where x is 0 and y equals 0. So let's draw that. So that point is at the origin, and this corresponds to when c is equal to 0. When c is equal to 1, that corresponded to the circle centered at the origin with a radius of 1. So drawing that, we'll get a circle center of the origin, radius 1. So something like this maybe. Let's say this is what we get when c equals 1. With c equals 2, we got a slightly larger circle. The radius was square root of 2. So c equals 2, slightly larger circle. Okay, so let's say that is when c equals 2. The radius of the circle is square root of 2. And even though the question didn't ask for it, I'm going to draw one more level curve. When c equals 3, when c equals 3, it turns out the radius of this circle is going to be square root of 3. So it's going to be slightly larger than the previous one. Slightly larger. Not a perfect circle, but something like this. So we got c equals 3. So notice that each time I'm increasing the value of c, these circles are getting a little bit closer and closer together. So these are our level curves. The example asking me to draw them. So when we draw a collection of level curves like this, all on the same graph, all on the same xy plane, we call this a contour diagram. So level curves are like a contour map. So contour maps, or sometimes called topographical maps, are maps of usually mountains that climbers can use to see, well, at different locations, what is the elevation or the altitude at that spot. Okay. So how can we use these level curves now? We can use the level curves to draw / describe the graph, the 3D graph. 3D graph. Okay, so I'm going to draw my 3D axes. So my z-axis, my x-axis slanted coming out of the page, the y-axis. Okay, the negative directions, so the negative y direction, negative z direction, negative x direction. So the way I read my level curves is, for example, with c equals 1, every single point on this curve where c equals 1 makes the output of my function be 1. So in other words, the z-coordinate, because that's what we call the output of a function of two variables, the z-coordinate is going to be 1 for every single point on this, this blue circle. Okay, so in fact, let me write that down. In general, the points on the same level curve have the same height. Okay, so I'm going to begin by drawing the c equals 0 level curve. So that means when this point is at the origin, when x is 0 and y is 0, the value of c tells me the height. Okay, so when x is 0 and y is 0 on my 3D graph, the height, or the z-coordinate, is also going to be 0. So that is at the origin. Okay. All right, so now let's draw when c equals 1. The height of every single point on this curve where c equals 1 needs to be 1. So I'm going to draw 1 on the z-axis. So I got to take this circle and make sure that every single point on it is 1 unit up. The z-coordinate is going to be 1. So imagine we first drew the circle on the xy plane like we have it in our level curves. So we're going to go 1 unit in the x direction, 1 unit in the y direction, -1 in the x direction, -1 in the y direction. If I drew a circle there, let's draw it with a dashed line. If I drew a circle, we'd have this. But we have to take every single point on the circle and move it up 1 unit. So this point is going to get moved up 1 unit. This point is going to get moved up 1 unit. This back point is going to get moved up 1 unit. And this point on the side is going to get moved up 1 unit. And if you connect those points, you get this circle that's lifted up to a height of 1. So you get something like this, a circle like that. So now if we do the next level curve, that was c equals 2, that's going to be a slightly larger circle that's been raised up 2 units. So I'm going to look at 2 on the z-axis. And this time I'm going to just draw it more directly. I'm going to draw a slightly larger circle that has its center point there on the z-axis. So that's going to look something like this. And I'll draw the back part of that circle. That back. Something like that. So this is making the surface of our region start to show up bit by bit. Because this bottom point corresponded to c equals 0. That blue circle at a height of 1 corresponded to c equals 1. And then the green circle at a height of 2 corresponded to the circle with c equals 2. So I can start to connect these, the edges of these, and I start to get a shape like this, going up, and start to connect the edges, start to get this sort of shape going up. And what this seems to give us is this sort of like 3D parabolic bowl. And that's the shape. That is the 3D shape right here. All right, so we've mentioned that level curves are like a contour map and that the points on the same curve have the same height. Moreover, the closer the level curves are, the steeper the graph is. For example, if I'm on the level curve where c equals 2, and I'm trying to travel a little bit to get to the level curve where c equals 3, I travel a much shorter distance to rise up by 1 unit to get from a height of 2 to a height of 3 than I would if I travel down to get to the blue curve and to get down to a height of 1. I would have to travel a much longer distance. So it's going to be steeper going from the height of 2 to the height of 3 than it would be going from the height of 2 to the height of 1. And that's happening with this parabolic shape. As it's curving upwards like this, it's getting steeper and steeper and steeper the higher up we go. So let's look at another example. But in this example, we're going to talk about slicing 3D shapes. So I want to describe the graph of this equation when it is first sliced by y equals -2. So what does that mean? So when you have a 3D shape and you're slicing it by some region, in this case y equals -2 is a plane, it wants us to find the intersection of that shape, x equals, it's z equals 3x squared minus 2y squared plus 7, and what it's getting sliced by, which is a plane, and the plane y equals -2. So to help us visualize this before we actually do the work, I want to show this in GeoGebra. So I have the equation of our surface typed in, so let's check that in. Okay, so this shape appears. So I'm going to rotate it a little bit so we can see it from different vantage points. Okay, so let's return it to kind of the orientation it was in. Okay, so we have this sort of shape here. And now I'm going to shade in the plane, y equals -2. So y equals -2, notice it goes through the y value, -2 here. So that is slicing this red surface. And we're sort of interested in, our example is asking, well, let's describe what that intersection looks like. And by looking at it from the picture, I see that it's sort of like curving here when the blue curve meets the red curve, curving down, curving down, curving down. And on the other side, if I look at it, it seems like it's curving up. It seems like it does this sort of thing. So it kind of looks like a parabola. So let's see if we get that algebraically. So if I'm trying to find the intersection of two things, the way we do that is I'm going to take one of these equations and substitute it into the other one. Okay, so let's plug y equals -2 into the other equation, z equals 3x squared minus 2y squared plus 7. So that gives us z equals 3x squared minus 2 times y is -2 squared, and then we have plus 7. So -2 times -2 squared, that's going to be -8. So this becomes z equals 3x squared Then negative 8 plus 7, that's a minus 1. So this looks really similar to if we had something like y equals 3x squared minus 1. And we know what shape that has. That would be in the shape of a parabola. This is also a parabola, but just a parabola on, in terms of the variables x and z. So this gives us a parabola, and the fact that the coefficient in front of the squared term is positive means it's an upward facing parabola. And I'm going to put quotes around upward. This is an upward facing parabola. I'm just putting the quotes around the word upward because when we're in 3 dimensions, depending on what direction something like a parabola is in, it can be a little bit less clear, like what direction is the upward direction. By upward in my case, I mean like the positive direction, so trending in the positive z direction. All right, so now let's slice it by x equals 0. So another plane. And we've actually graphed x equals 0 before. Remember, x equals 0, this was the yz plane, the plane that contains the y and the z axis. So this time we need to plug in x equals 0. Plug in x equals 0. Let's zoom out a little bit so I can see my original equation. So I can plug into that now. So this gives me z equals 3 times 0 squared minus 2y squared plus 7. Or simplifying, z equals negative 2y squared plus 7. So this is another quadratic, so another parabola shape. Because once I've plugged in a value for one of the variables, like x equals 0, now this intersection, or this slice, is now a two-dimensional shape. So this is a parabola, but because that leading coefficient is negative this time, it is a downward-facing parabola. Downward-facing parabola. All right, so one more of these. What if I sliced it by z equals 1? So this time we are going to plug in z equals 1. In doing that, we get 1 equals 3x squared minus 2y squared plus 7. And I'm going to rearrange this to keep all of the variables on one side and all the numbers on the other side. So I'll move the 1 over to the right-hand side to keep the number positive. So that'll give us 6 on the right, and then all the variables over to the left. So we'll get 2y squared minus 3x squared equals 6. And this is where we have to remember some of our graphs from algebra. I'd encourage you to pause the video for about 30 seconds and see if you can remember, well, what type of graph is this? 4, 3, 2, 1, pause the video. Pause it for 30 seconds and see if you can identify what type of graph this is, what shape it has. All right, so hopefully you did that. Hopefully you paused it for about 30 seconds to think about that. It turns out this is a hyperbola. So this is really a blast from the past, a hyperbola. So if we use GeoGebra to verify that, I've typed in z equals 1 here. So if I shade that in, notice that it gives us this plane z equals 1. It's 1 unit above the xy plane. So that was the xy plane, this thing in gray, this flat one. Z equals 1 is 1 unit higher. But notice that the intersection, if I trace it out, has one part over here. And there's also one part of the intersection of the red and the blue over here. And that's the signature of a hyperbola. So as a brief review, recall that if you have an equation of the form ax squared plus by squared equals c, where the a, the b, and the c are all positive numbers, that will turn out to be an ellipse. And if it's slightly different, if one of these squared terms has a negative coefficient in front of it, so either ax squared minus by squared equals c, or the other way, by squared minus ax squared equals c, then both of those give us, as we saw here, a hyperbola. So finally, in terms of our goals for this section, I went out of order here a little bit. We've talked about how to graph more complicated functions using cross-sections and level curves. In the next video, we'll do an example where we tie in all of these concepts. It'll be a matching question where I'll give you a list of functions and a few graphs, and we have to match which function goes with which graph in 3D space.